this video, we'll dive into a practical example that demonstrates how to perform word count on Kafka stream of tweets using PyFlink and store the results in Elasticsearch to be visualized with Kibana. Now, let's get started. In this video, we'll leverage PyFlink to process a stream of tweets and perform word counts by analyzing the word count. We can identify the most frequently occurring words or phrases in the dataset. This information can help us to understand the popular topics or subjects being discussed. For example, if words like technology, innovation, and startup have frequencies, it indicates that tweets focus on the tech industry. Also, analyzing word counts trends can help businesses and researchers stay informed about emerging topics, track the life cycle of trends, and make data-driven decisions based on the evolving interests and preferences of their target audience. We'll take a through this word count streaming architecture pipeline, where we will leverage the power of Kafka, Flink, Elasticsearch, and Kibana. Let's dive in. Our pipeline begins with Kafka, a high-throughput distributed messaging system. We connect Kafka to the Twitter API, allowing us to ingest a continuous stream of tweets in real time. This ensures that we have a constant flow of data to work with. Once the data enters Kafka, it's time for Flink, a powerful stream processing framework. Indeed, Flink enables us to process the incoming stream of tweets in real time, applying various transformation and computations. In our case, we'll be performing word count analysis to identify the frequency of words within the tweets. Now that we have processed the data, we need a robust and scalable storage solution. Here comes Elasticsearch, a distributed search and analytics engine. We index and store the processed data in Elasticsearch, which allows for efficient querying and retrieval. But data alone is not enough. We need to make sense of it and visualize the results. That's where Kibana comes into play. Kibana is a powerful data visualization tool that seamlessly integrates with Elasticsearch. It provides real-time dashboards and interactive visualizations in real time. It will allow us to monitor the word counts analysis results as they unfold. And there you have it, the word count streaming architecture pipeline. With Kafka, Flink, Elasticsearch, and Kibana working together, we can ingest, process, store processed data, and visualize streaming data in real time. There are a few prerequisites you need to ensure. Let's go over them briefly. Firstly, make sure you have Apache Flink installed and set up correctly. Apache Flink is the powerful stream processing framework we'll be using for our pipeline. And of course, Apache Kafka must be installed already. Next, we need to install the necessary Python dependencies. This includes PyFlink, NLTK, and codecs. You can use popular package managers like Pipe or Conda to install these dependencies. Then, to enable NLTK's stop words functionality, we need to download the required NLTK resources. This can be done easily by running a simple command in a Python shell or scripts. Just execute NLTK that downloads stop words to obtain the necessary stop word resources. Also, ensure that you have Kafka and Elasticsearch properly set up as I told you just now. Kafka will be used to ingest data from Twitter API and Elasticsearch will be used to store and access the processed data. And make sure the cluster are accessible. Lastly, we need to have the required Flink connector jar files. These include Flink SQL connector Kafka and it depends on the version of Scala and the Flink that you have. In my case, I have Scala 2.11 and Flink 1.4.14. It depends on your cluster. And also Flink SQL connector Elasticsearch. In my case, I have Elasticsearch version 7. Now let's move to explaining the stream in Python code. First, we need to import the necessary modules and classes from the required libraries. It's like a reminder, I just said that to enable NLTK stop words functionality, we need to download the required NLTK resources. This can be done easily by running simple command in a Python script, shell script. Just don't forget to execute nltk.download stop words to obtain the necessary stop word resources. Just nltk. Next, we define a function called word count processing that encapsulates our entire word count process. Inside this function, we set up the PyFlink environment and create a table environment. We then specify the necessary connector and format jars for our PyFlink environment using the pipeline.jars configuration. Now, let's define the source and sink tables. We use data definition language, DDL, to specify the structure and properties of these tables. The source table is responsible for reading data from Kafka topic, and the sink table is responsible for writing the word count results to Elasticsearch. For the source DDL statement is used to define the source table, which represents the data stream of data we want to process. Here is a breakdown of the statement. Create table source table. This line specifies the name of the table we are creating, which is source table. EDSGR username, tweet location, retweet, followers, link. These lines specify the schema of the source table, listing the names and types of the columns. In this case, the table has columns named EDSGR, username, tweet, location, retweet count, followers count, and link. With this keyword introduce the option and configurations for the table. Connector. This line specifies that this table is connected to a Kafka topic. Topic is equal to my topic chest. This line specifies the name of the Kafka topic from which the table will read data. Properties.bootstrap.server. This line specifies the bootstrap servers for the Kafka cluster, which are the addresses used to establish the initial connection to Kafka. And the properties.group_id. This option specifies the group ID that the table will use when reading data from Kafka. The consumer group is responsible for coordinating the consumption of messages from the topic. Scan.startup.mode is equal latest offset. It can be also earliest offset. This option specifies the startup mode of the table. In this case, it starts reading from the latest offset in the Kafka topic. Format JSON. This option specifies the format of the data in the Kafka topic, which is JSON in this case. Now, I will explain the sync DDL. This DDL statement is used to define the sync table, where we will store the word count results. Here is a breakdown of the statement. Create table, sync table. This is the first line, which specifies the name of the table we are creating. In this case, it's sync table. Word varchar number begins. These two lines define the schema of the sync table, listing the names and types of the columns. In this case, the table has columns named word and number. With this keyword introduced options and configuration for the table. And connector, it's in this case Elasticsearch 7 because I have the Elasticsearch 7 installed. This line specified the table that the table is connected to Elasticsearch version 7. Index. To define the Elasticsearch index, we'll choose as a name demo word count. Then we have hosts for the Elasticsearch host name. These two execute SQL lines execute the DL statement for creating the source and sync table respectively. In this word count processing pipeline, the data goes through a series of steps to ensure its cleanliness and prepare it for analysis. Firstly, the text is pre-processed to remove escape characters, URLs, no ASCII characters, user mentions, and retweet tags. Then, the pre-processed text is split into individual words. After that, the words are normalized by removing punctuation to treat variation of the same word as identical. Common stop words are then removed to focus on the most relevant words. Finally, the remaining words are counted to determine their frequency, and the resulting word count table is stored for further analysis. Think in this code will explain pre-processing the data. Indeed, to ensure that our analysis is based on a clean and meaningful text, we need to pre-process the tweet data. We define a user-defined function, UDF, called pre-process text that removes escape characters, URLs, no ASCII characters, user mentions, retweet tags, and perform various other cleaning steps. This UDF prepares the tweet text for further analysis. Creates a new table called preprocess table by selecting the tweet column from the existing source table and applying a preprocessing function called preprocess text to each element in the tweet column. Once the data is preprocessed, we split the text into individual words. We define another user-defined function, UDTF, called split, that takes a row of text and yields each row as a separate row. This step allows us to work with individual words for the word count analysis. Now we'll move to normalizing the words. Indeed, before counting the words, we need to normalize them by removing punctuation. We define a user-defined function, UDF, called normalize, that takes a word as input and return the word with punctuation removed. So, next step is removing stop words. Indeed, to focus on the most relevant words, we remove common stop words from our analysis. We define a scalar function called remove stop word that uses the NLTK library to obtain a set of English stop words. This function checks if each word is not in the stop word set, effectively removing them from the analysis. And then the next step is computing the word count. With the data pre-processed and stop words removed, we are ready to compute the word count. We use the table API of Flink to group the words and count their occurrences. The resulting word count table is then reached to the Elasticsearch sync table. So, congratulations! you have successfully learned how to perform word count on stream of tweets. Indeed, it's the stream of Kafka using PyFlink. This technique can be applied to various real-world scenarios, such as detecting trends. Now let's run this PyFlink streaming code. We run it in Visual Studio Code, and we can see here in the console terminal that the schema printed of the source table run the Kafka producer. This producer was created in the section of Twitter Kafka Hands-on in Python. We run it in Python and data stream is running from the Twitter API. Now we can see here that the index, new index is created automatically from this PyFlink code. We'll now create, Elasticsearch index. Now we have to create Kibana index. We'll copy and paste the name of this Elasticsearch index, then click on create Kibana index or create index pattern. We'll go to the Kibana dashboard to create a visualization about the word count. We'll select the Elasticsearch Kibana index, which is demo word count, and we drag and drop the data file, which are word and number. We'll choose a meaningful visualization type. In this case, we'll choose, I think, the maximum of the number of frequencies of the words, and we'll show it in a table because it's the easiest and main way for visualization. We choose 100 word, and we need to classify and order the words by the number of frequency of each word. We can give a title for this to word, and also we change the maximum of number to count. That's it. It's easy. And here we give a title for this visualization. We can give it as a name word count. Save it, and I will create a word cloud, because word cloud can show interesting insights. And here we need to define tag cloud, yeah, and we chose the index. Then in buckets we click on tags, then on terms we select a file which is number, and the size of this cloud 100 word. The problem here is that I think the problem is in the file. We should not choose number. We must choose a keyword, yeah, and that we can see now the keywords. We save it, and here we have the word cloud in the Kibana dashboard. It will be a dynamic dashboard which will be updated in real time as the data flow come. And we give it a title, word cloud. Yeah, in tweets. Give it a good size to for the visualization to be clear. Now we will run the Kafka producer to produce data stream in real time, and we will see the visualization in Kibana dashboard that will be updated in real time also. As you see, there is an update in the word cloud and also in the this table related to the word cloud in real time as the data stream comes. As you see, the data is updated, the word cloud is updated each time there is new data. So congratulations, the word count data stream with the Kafka, Flink, Elasticsearch and Kibana is working fine in real time. Thank you for watching.